In 1019, Arthur Eddington shipped a telescope to an island off the coast of Africa and photographed stars near the solar disk during a total eclipse. The stars were not where they should have been. They had shifted, not because they had moved, but because the mass of the sun had bent the light they were sending our way. The light traveled in a straight line, but a straight line through curved space is a curve. This was noticed by Pierre de Fermat, the same Fermat whose last theorem tormented mathematicians for 3.5 centuries. His principle about light is simpler but equally profound. Light always finds the route that takes the least time, not necessarily the shortest distance, the fastest connection between 2 points. When light moves through water, it slows down. So the optimal path, the one that minimizes total travel time, is no longer a straight line through the boundary. It's an angled path that spends less time in the slow medium. The straw looks bent because light is being efficient. And here's a thing worth sitting with for a moment. Fermat announced this principle in 1662. At the time, nobody could explain why it worked. Light doesn't think. It doesn't calculate. It doesn't try the slow routes first and reject them. It simply arrives having taken the optimal path every single time. This struck many of Fermat's contemporaries as almost theological, as if light knew where it was going before it set off. It would take another 2 centuries before physics developed the mathematical language to explain why minimum principles work. The short answer is that nature doesn't actually compute optimal paths in advance. Paths that are close to optimal interfere constructively with each other. Paths that are wildly off cancel themselves out. The minimum emerges from the physics, not from intent. But in everyday life, the principle is practically magical, and it works. This isn't unique to light. In physics, there's a broader idea called the principle of least action. Any particle moving freely through space follows the path that minimizes a certain quantity. In empty, flat space, that minimum path is simply a straight line. That's almost definitionally obvious. If nothing interferes, why would anything curve? The principle of least action is one of those ideas that keeps reappearing across all of physics, in forms that seem unrelated until you look closely enough. Classical mechanics, quantum field theory, electrodynamics, optics, every time the same underlying pattern. Nature is, in some precise mathematical sense, economical. It doesn't waste. A planet orbiting the sun, an electron jumping between energy levels, a photon crossing a lens, each follows the path that extremizes a specific quantity. The details differ. The principle doesn't. Richard Feynman spent much of his career thinking about why. His answer, in the language of quantum mechanics, is that particles actually take all possible paths simultaneously. Most paths cancel each other out through interference. They're like waves slightly out of phase, adding to zero. Only near the classical path, the optimal one, do the contributions reinforce each other. The classical trajectory, the straight line, the parabolic arc, the Keplerian orbit emerges as the path where the phases align. The minimum isn't imposed from outside, it's what's left after everything else cancels. But to understand why light bends near massive objects, we need to take that principle and push it further than Fermat intended. So here's the question. Suppose space really is empty. No atmosphere, no dust, no gas, no medium of any kind. You have a vacuum in the strict sense, and you send a beam of light across it. The beam curves. What does that mean? It means space itself is not flat. In modern physics, curved light in a true vacuum is not a mystery to explain. It's a diagnostic. It's the symptom that tells you the geometry of space-time has changed. There is no other explanation. A photon in empty space follows the shortest available path, what physicists call a null geodesic. If that path curves, the space is curved. The logic is airtight, and it's one of the most striking inversions in the history of science. Instead of asking why something deflects light, we ask what kind of geometry would produce exactly this deflection, And space does curve near mass. The more compact and heavy an object, the stronger the curvature it creates around itself. Near Earth, the effect is tiny. Near the Sun, measurably larger. Near a neutron star, significant enough to visibly distort the light paths of background objects. And near a black hole, the curvature becomes so extreme that light itself can orbit or disappear entirely. To understand why mass curves space-time, you need Einstein's insight that gravity and acceleration are, locally, the same thing. Imagine you're inside a sealed box. No windows, no instruments except a scale you're standing on. The scale reads your normal weight. Are you standing on Earth? Or are you in a rocket accelerating at exactly 9.8 meters per second squared through empty space? There is no experiment you can perform inside that box to tell the difference. Gravity and acceleration are equivalent. Now tilt the thought experiment. In a rocket accelerating upward, a beam of light entering from the side will appear to curve downward, because by the time the light crosses the room, the floor has accelerated up to meet it. The light path is bent. But if gravity and acceleration are the same thing, then gravity must also bend light. Not as an optical illusion, not through some atmospheric effect, as a fundamental consequence of what gravity is. Einstein saw this in 1907, years before he had the full mathematics to describe it. He called it the happiest thought of his life. The full theory came 8 years later. Those 8 years were not smooth. Einstein started with an intuition and spent nearly a decade trying to find the right mathematical language to express it. He taught himself Riemannian geometry, the mathematics of curved surfaces, developed by Bernhard Riemann in the 1850s for purely abstract reasons, with no application in sight. Riemann had asked a simple question: what is a geometry in which parallel lines can converge, in which the angles of a triangle don't add up to 180 degrees, in which the shortest path between 2 points is not a straight line? His answer was a general framework for describing curved spaces of any dimension. Einstein picked up this framework half a century later and used it to describe something Riemann never imagined: the geometry of physical spacetime itself. The full theory said something more radical than just gravity bends light. It said gravity is not a force at all. It's the curvature of spacetime. Massive objects warp the geometry of the four-dimensional fabric around them, and everything else, planets, photons, clocks, simply follows the straightest possible path through that warped geometry. What we call gravitational attraction is objects moving along geodesics in curved spacetime. They're not being pulled. They're following the shape of the space. Mercury demonstrated this before anyone tested it with light. The innermost planet's orbit doesn't quite close. It precesses, the whole ellipse slowly rotates, so that Mercury traces a kind of spirograph pattern over centuries, rather than retracing the same ellipse indefinitely. Newton's theory could account for most of this precession, caused by the gravitational influence of the other planets. But there was a residual of 43 arcseconds per century that Newton couldn't explain. Astronomers had proposed all kinds of patches: a hidden inner planet, a slight oblateness of the sun, dust in the inner solar system. None worked cleanly. When Einstein calculated what his new theory predicted for Mercury's precession, he got exactly 43 arcseconds per century. He said the result gave him palpitations. He couldn't sleep for 3 days. This gives us a way to test the theory with light. Take the sun. If general relativity is right, the curved spacetime around it should deflect passing light, including light from distant stars that happens to graze the solar edge. Look at the positions of those stars when the sun is far away from them in the sky. Then wait for a solar eclipse, when you can actually see stars near the sun. Their apparent positions should shift. The starlight, bending around the solar mass, arrives at your eye from a slightly different angle. The first attempt to measure this was made in 1919 during a total solar eclipse visible from the island of Principe off the coast of West Africa. Arthur Eddington led the expedition. The circumstances were difficult. The sky was partly cloudy, the instruments were basic by modern standards, and the analysis required careful corrections. But the result matched Einstein's prediction. The news traveled fast. Overnight, Einstein became famous in a way that very few scientists ever have. The Times of London ran the headline, "Revolution in Science, New Theory of the Universe, Newtonian Ideas Overthrown." Whether Eddington's original measurement was precise enough to truly distinguish between Newton and Einstein is debated by historians of science. Some argue the error bars were too large to be decisive, and that Eddington, a convinced Einsteinian, may have been too quick to dismiss inconvenient data. That argument is fair, but it's also somewhat beside the point. The experiment set a direction. Better instruments, better eclipses, better analysis followed, and every measurement has agreed with general relativity. But the sun isn't cooperating cleanly. It has a corona, a diffuse halo of charged gas and plasma extending into space. That corona is a medium, and light bends in media too, so the deflection you observe is a mixture, part geometry, part atmosphere. How do you separate them? By using the geometry itself. Draw imaginary concentric rings around the sun. For each ring, average the apparent shifts of all the stars it contains. Stars close to the sun deflect more, stars farther out deflect less, and the way that deflection falls off with distance follows a specific mathematical law. That law, that curve of decreasing displacement, can be compared to what the theory predicts, and it qualitatively matches general relativity. Here's the subtlety, though. Newtonian gravity also predicts light deflection, at least if you allow yourself to treat a photon as a particle with an effective mass derived from its energy using E equals mc squared. That hybrid calculation gives a deflection of about 0.87 arcseconds. General relativity predicts 1.75, exactly double. The doubling is not a coincidence. It comes from the fact that general relativity curves not just space but time as well, and both contributions add together with equal weight. The spatial curvature alone would give the Newtonian result. Adding temporal curvature doubles it. That factor of 2 is the real test. And here's the uncomfortable truth. Current instruments cannot cleanly resolve that distinction for the sun. We can confirm the deflection exists. We can see it qualitatively agree with GR, but pinning down exactly whether it's 0.87 or 1.75 arcseconds, the measurements are still not precise enough. General relativity, of course, rests on much firmer ground elsewhere. Take the GPS system. Your phone knows where you are too within a few meters. That precision depends on clocks aboard satellites staying synchronized with clocks on the ground. Relativity says they can't, automatically, not without correction. The satellites move fast, which special relativity says slows their clocks. And they're higher up, where spacetime is less curved, which general relativity says speeds their clocks. The two effects don't cancel. They have to be calculated and corrected for every day. If they weren't, GPS positions would drift by kilometers per day. Every time you navigate somewhere, you're implicitly trusting general relativity, or take gravitational lensing. When light from a distant galaxy passes near a massive foreground object, another galaxy, or a cluster of galaxies, the curved spacetime acts like a lens. The background galaxy's light bends around the mass and is focused toward us. We see multiple images, arcs, or in perfect alignment, a complete ring, what astronomers call an Einstein ring. The effect isn't subtle. It's visible in ordinary telescope images. Cosmologists use gravitational lenses deliberately as natural telescopes to see objects far too dim and distant to observe any other way. And gravitational lensing does something even more remarkable. It lets us map mass we can't see. Most of the matter in the universe doesn't emit light. It doesn't absorb light either. It interacts with nothing except through gravity. We call it dark matter, which is really a name for our ignorance. We know it's there because of how it bends light. When astronomers map the distribution of gravitational lensing across a galaxy cluster, they're tracing the shape of something invisible. The lensing patterns show mass concentrated in places where there are no visible stars, no gas clouds, nothing that any telescope in any wavelength can detect. The geometry of light is the only instrument we have, and it tells us that the matter we can see, stars, galaxies, gas, dust, is only about a sixth of all the matter that exists. Now, the deeper point about light geodesics goes further than just measuring deflection. Physicists use them structurally. Think of how we map the surface of Earth. We draw a coordinate grid, meridians, parallels. Those lines don't physically exist, but they tell you how the surface is shaped. You can do the same thing for curved spacetime. Trace how light would propagate through a region of space near a massive object. Those imagined light paths form a coordinate grid, and how much that grid bends, how much it deviates from the flat, straight, regular grid you'd expect in empty space, tells you precisely how much spacetime is curved. It's the same logic as reading a topographic map. The closer the contour lines, the steeper the slope. The more distorted the light path grid near a massive object, the stronger the curvature. General relativity uses exactly this. The metric, the mathematical object that describes how distances and time intervals are related across spacetime, is essentially a precise description of that distorted grid. Solving Einstein's equations means finding the metric, finding the grid, for a given distribution of mass and energy. Carl Schwarzschild found the first exact solution in 1916 while serving on the Russian front during World War I. He solved Einstein's equations for the space-time around a perfectly spherical, non-rotating mass, a star, in the simplest approximation. The solution is called the Schwarzschild metric, and it describes something peculiar. At a certain radius, now called the Schwarzschild radius, the metric behaves strangely. For an ordinary star like the Sun, that radius is about 3 kilometers, well inside the star, where the vacuum solution doesn't apply anyway. But if you could compress the Sun's entire mass into a sphere 3 kilometers across, the Schwarzschild radius would be at the surface, and spacetime outside it would curve so severely that not even light could escape. Schwarzschild found the mathematical description of a black hole 40 years before anyone took the concept seriously. At the event horizon, the surface at the Schwarzschild radius, something remarkable happens to light. A photon trying to escape from exactly that boundary makes no progress. It's like running up an escalator that moves precisely as fast as you do. You expend all your energy and stay in place. Below the horizon, no path exists that leads outward. The geodesics, the straightest possible paths through that space-time, all point inward. Not because the gravity is strong in any familiar sense, but because the geometry itself is oriented inward. There is no direction that leads out. Now, a word about the speed of light, because this is where things get routinely misunderstood. The statement that the speed of light is constant, that it's the same in all reference frames, is often presented as a universal truth. It isn't quite. It's true in flat spacetime when you switch between inertial reference frames. The moment you move to a non-inertial frame or to curved spacetime, the speed of light as measured using coordinate time and coordinate distance can vary from point to point. What remains true, always, is that light is the fastest thing locally. No particle, no signal has ever been observed to outrun a photon in the same region of space. The constancy of the speed of light is not a postulate of general relativity. It's a consequence of flat Minkowski geometry, the geometry that special relativity describes. In that geometry, the symmetry between inertial frames forces the speed of light to be the same for all of them. Take away the flatness, and the specific constancy goes away with it. The local supremacy of light does not. This becomes critical when we talk about the expanding universe. A common way to picture cosmic expansion is an inflating balloon with dots on its surface representing galaxies. As the balloon expands, the dots move apart. Now, if the balloon expands fast enough, Two dots on opposite sides can be moving apart at a rate faster than the speed of light. This observation is real. It's confirmed. Distant galaxies are receding from us faster than 300,000 kilometers per second. Edwin Hubble first measured the systematic recession of galaxies in 1929. What he saw was that the further a galaxy is, the faster it moves away, a linear relationship now called Hubble's law. Since then, we've measured that expansion with increasing precision. And in 1998, observations of distant supernovae revealed something unexpected. The expansion is not slowing down. It's accelerating. Something, dark energy most likely, is pushing the universe apart faster and faster over time. What dark energy is, nobody knows. It fills space uniformly. It exerts a kind of negative pressure, and it constitutes about 68% of the total energy content of the universe. It was Einstein who first introduced a term into his equations that could play this role, the cosmological constant, which he added and then removed, and then apparently regretted removing. Whether dark energy is the cosmological constant or something more dynamic that changes over time is one of the central open questions in cosmology. We know it's there because of how the universe expands. We don't know what it is. So some galaxies are receding at multiples of the speed of light. And people sometimes read this as a contradiction. Isn't relativity supposed to forbid faster than light motion? The confusion comes from mixing two different geometries. When the theory of relativity forbids faster than light travel, it's talking about motion through flat space-time, like a rocket burning fuel to cross a region of empty space. What cosmology is measuring is something different. The rate at which the space between galaxies is growing due to the geometry of curved, expanding spacetime. You can't subtract those velocities and compare them any more than you can compare the curvature of a mountain slope to the curvature of a balloon and call them the same number. On the balloon's surface, within that curved spacetime, light is still the fastest traveler. The galaxies are not outrunning light. The space between them is expanding. Those are not the same thing. There's a practical consequence that makes this concrete. Light from galaxies receding faster than the speed of light can still reach us, but only if they were within a certain distance when they emitted it. The universe has an observational horizon. Beyond it, the expansion is carrying things away faster than any signal can close the gap. Not because relativity is broken, but because the geometry is such that the distance is growing faster than light can traverse it. The light from those regions will never arrive. They are, in the most literal sense, unreachable, not by law, but by geometry. And the horizon is not fixed. Because the expansion is accelerating, the region from which we can receive new information is actually shrinking over time. Galaxies that are now inside our observable universe will eventually cross the horizon. Their light emitted today will simply never reach us. Future civilizations, billions of years from now, will look out at a sky with far fewer galaxies. The ones that have crossed the horizon will be gone, not destroyed, but cosmologically severed, isolated, inside an expanding geometry that has outrun any possible communication. What looks to us like a universe full of billions of galaxies will look to observers in the deep future like a universe that is almost empty. The real postulate, the one that doesn't bend, is this: in any spacetime, in any frame of reference, light is locally the fastest. Its coordinate speed can vary. Its independence from the observer's motion is a consequence of flat Minkowski geometry, not an absolute law of the universe. In curved spacetime, that specific constancy doesn't hold. The local supremacy does. And there's one more consequence of curved spacetime worth naming, because it ties everything together. Not just space curves near a mass. Time does too. A clock running near a massive object ticks more slowly than the same clock running far away. The gravitational redshift. The fact that light climbing out of a gravitational field loses energy and shifts to longer wavelengths is the photon version of this. Light leaving the surface of a dense star arrives at a distant observer stretched. It has climbed out of a gravitational well, and the geometry of that climb is recorded in its frequency. This was first directly measured in 1959 by Robert Pound and Glenn Rebka in a tower at Harvard University. They used gamma rays, and they measured the frequency shift between the top and bottom of a 22-meter tower. The effect is so small over that distance that it took specialized atomic physics to detect it. But they found it. It matched the prediction of general relativity. The experiment has since been repeated with far greater precision, including by flying atomic clocks on aircraft and even on cargo rockets. Every result confirms the same thing. Clocks at lower gravitational potential run slow. The effect is real, it is measurable, and it is baked into the infrastructure of modern technology. This is not a small effect at GPS scales. The altitude difference between a satellite and the ground produces a time dilation of about 45 microseconds per day from gravity alone. Special relativistic time dilation from the satellite's orbital speed subtracts about 7 microseconds per day. The net correction is roughly 38 microseconds per day. 38 microseconds sounds negligible, but light travels about 11 kilometers in 38 microseconds. An uncorrected GPS system would accumulate 11-kilometer position error per day. By the end of a week, your navigation app would be placing you in a different city. There is one more test that deserves mention because it confirmed the most dramatic prediction of general relativity, one that Einstein himself doubted could ever be observed. The theory predicts that accelerating masses should radiate energy in the form of gravitational waves, ripples in the fabric of spacetime itself, propagating outward at the speed of light. Two black holes orbiting each other, spiraling inward, finally merging, such an event would send a gravitational wave through the universe, stretching and squeezing space as it passed. On September 14, 2015, the LIGO detector in Louisiana recorded a signal. It lasted about 0.2 seconds. It was the gravitational wave from two black holes merging, 1.3 billion light-years away. The collision released more energy in that fifth of a second than the sun will radiate in its entire 10-billion-year lifetime, all in the form of gravitational waves. The stretching of space that reached Earth was about 1,000th the diameter of a proton. LIGO measured it. General relativity predicted the exact waveform, and the signal matched it perfectly. Light, then, is more than just something we see by. It's the geometry of the universe made visible. It traces the shortest paths through whatever space it moves through. In flat space, those paths are straight. Near a star, they curve. Near a black hole, they spiral. And by watching where light goes, where it bends, how much, by what pattern, we can read the shape of spacetime the same way a cartographer reads the contours of a mountain from the lines on a map. The universe keeps its own coordinate grid. It's written in light. And learning to read it, from Fermat's observation about a straw in water, to gravitational waves from colliding black holes a billion light-years away, is one of the longest and strangest journeys in the history of human thought. A journey that began with a bent straw and ended with a theory that tells us how the universe began, how it will end, and why your phone knows where you are.